Alright, here is a video about how Bahtinov masks work for telescopes. So before we can begin talking about how it works, we need to know a little bit about diffraction spikes. So this is a Schmidt-Cassegrain telescope. The front of it has a piece of glass holding on the secondary mirror. But on a Newtonian telescope, it has metal bars holding it in place. So if we look through a Schmidt-Cassegrain telescope at a star, it's going to be perfectly circular. But if you look at a star through a Newtonian telescope, it's going to have these diffraction spikes on it. And these spikes are caused by the bars holding on the secondary mirror. But a thing to remember is that the diffraction spikes happen 90 degrees from the direction of the bar. So this horizontal red bar is causing the vertical red spike in the star, and vice versa, the vertical green bar is causing the horizontal green spike on the star. So on a Bahtinov mask, half of it creates this vertical spike, and the other half has these two slanted spikes. And we'll get back to that in just a moment. But let's imagine a Bahtinov mask that just has the horizontal spines on it. When you look at a star through it, the diffraction spike is going to happen off to the side. But as you focus closer and closer, the diffraction spike also gets closer and closer to the middle until the star is focused perfectly down to a point where the diffraction spike is going to be directly through the center. Now, if we look back at the Bahtinov mask and we just consider the center of these diffraction spikes, as you focus down, these two are going to get closer and closer to each other. So when your star is unfocused, you're going to have the vertical bar all the way off to the side and the X shape all the way off to the side. But as you get closer, the vertical bar and the X are going to approach the middle until you're perfectly focused where they're both exactly in the middle. And that's how Bahtinov masks work.